Hello everyone. We are the students from PHG College of Technology. Here we are going to do a project on computer vision based on the real time application. The topic we are going to discuss in this video is measurement of distance and size of the object. We use OpenCV and Python as the main source to do this. Here these are the team members who have done this project. Let's go with the presentation.
First of all, let's see what is object detection. Object detection is a computer vision technique for locating instance of object in image or video. Object detection algorithms are mainly of two types, machine learning and deep learning, to produce meaningful results. When a human looks at an image or a video, we can recognize and locate the object of interest within a matter of moments. The goal of detection is to replicate this intelligence using a computer. Every object class has its own special feature that helps in classifying the classes. For example, all circles are round. Object detection uses these features. Here we mainly use the OpenCV to locate an image. Now let's see what an OpenCV means. An open source computer vision is a library of programming functions mainly aimed at real-time computer visions, originally developed by an Intel. The OpenCV is written in C++ and its primary interface is C++, but it still remains a less comprehensive, though extensive older C interface. There are bindings in Python, Java, MATLAB and Octave. OpenCV was built to provide a common infrastructure for computer vision applications and to accelerate the use of machine perception in commercial products. The OpenCV mostly leans towards the real-time vision applications and takes advantage of MMX and SSE instructions. The OpenCV application areas include 2D and 3D features toolkit, ego motion estimation, facial recognition system, gesture recognition, human-computer infrastructure, mobile robotics, motion understanding, object identification, segmentation and recognition, stereophysis and depth perception of two cameras, structure from motion, motion tracking, and augmented reality.
Okay, now let's see how to find the distance of an object from the camera and what are the formulas used to find this distance. So under this topic we cover how the object detection technique is used to find the distance between the object and the camera, and also how to find the object size. So for measuring this we apply a concept called triangle similarity. So for finding this distance, first we need to calculate the focal length of the camera. So for example, if I have a object with a known width W and I place this marker some distance d from my camera, then I take a picture of that object using my camera and then measure the apparent width in pixel p. So this allows me to derive the focal length f of my camera. So the formula is f is equal to p into d by w, where this p is apparent width in pixels, then d is distance of object from the camera, then w is known width of object. So by applying this formula, let's see an example. I place a standard piece of 8.5 cross 11 inches piece of paper at the distance of D is equal to 24 inches in front of my camera and take a photo. So I get the pixel like 248 pixels. Then substitute all the values in the focal length formula. Then you get the value as 543.45 as focal length. So in the next step, we apply the same concept, that is triangle similarity, to find the distance of the object to the camera. So the formula is W into F by P. So now I move my camera 3 feet or 36 inches away from my marker and again take a photo of the same piece of paper. So now I get the width as 170 pixels. So when the camera distance between the camera and the object becomes larger, the pixel value becomes lesser. So we know all the values, substitute everything, and the focal length value, we found it in the first step. So substitute that and we get the distance as 35 inches. So once the focal length of the camera is calibrated, we can measure the distance of the object with the known distance and width. Okay, now let's see the program which is used to measure the distance of an object. There are 7 steps in this. In the first step, we need to import all the necessary packages. Then in the second step, we have to find the object in the image. Then finding the contours. Then in the fourth step, calibrating and computing the focal length. Then in the fifth step, distance calculation function. Then sixth step is we have to load images to find the accuracy. Then if we follow all these steps, we'll get a final results. So the first important step is to import the necessary packages that we want to be imported in a program, so that we can use the functions in the library. So immutils is nothing but it's a library file which is used to perform image processing functions like thresholding, grayscale image conversion, adaptive thresholding, and edge detection. NumPy is nothing but a numerical function which is used to perform the numerical function in a program. So if these packages has to be imported in a program to perform the further processes. So after importing all this, we have to convert the image to grayscale, blur it, and detect edges. So in the first line, gray is equal to cv2.cvt color into image cv2.color _bgr to gray. So in this line, the image will be converted to grayscale. Then the second line, gray is equal to cv2.gaussian blur gray 5,0. So in this line, the image get blurred. Then in next line, edged is equal to cv2.canny gray 35,125. So in this line, we can detect the edges. So next step, we have to find the contours in the edged image and keep the largest one. Now let's assume that this is our piece of paper in the image. So for finding the contours, we have to type these three lines, and then after typing these, we have to return it after computing the bounding box of the paper region. So finally return cv2 dot minimum area. In the before slide, all first 3 steps are done. So now let's see the fourth step, that is we have to calibrate and find the focal length. So first, for finding this, we have to initialize all the known values. That is, known distance in this case is 24 inches and known width is 12 inches wide. Then we have to find the focal length. For that, first we have to load the image that contains an object that is known to be 2 feet from our camera, then finding the paper marker in the image, then initializing the focal length. So for finding this focal length, we have to first load the image, then find the paper marker. Then focal length formula is marker into known distance by known width. Then we'll get the focal length. We have computed that. Then in the next step, we have to calculate the distance to the camera. So for that, distance to camera, known width, focal length per width, we know we have found in the before step. Then computing and return the distance from the marker to the camera. For that, return known width into focal length by per width. So in the last step, we have to load the images to find accuracy. First, loop over the images. For that, we have to give this line. Then next, we have to load the image, find the marker in the image, then compute the distance to the marker from the camera. Then for finding that distance to camera, we have to give these 3 lines: image, marker and inches is equal to distance to camera, all these steps. Then finally we have to draw a bounding box around the image and display it. So if we give all these steps, finally we'll get the image like this. As I said before, I kept the camera 2 feet away from the object and I get this image.
Measuring size of an object in an image. Concept is pixel per metric ratio. We are going to use image pixel as a value to get the size of an object. So we are using a reference object which is used as a calibration one. Let's see the property of a reference object. We should know the dimension of an object in a measurable unit. We should be able to easily find these reference object in an image either based on the placement of an object or via appearance. Reference object should be unique. Here we use coin as a reference object and it will be the first contour for calibration and it will be in the leftmost corner. Let's find pixel per metric ratio. Pixel per metric ratio is equal to object width by known width. The coin has known width of 0.955 inches and now suppose that our object width is computed be 150 pixel. Therefore, pixel per metric ratio is equal to 150 pixel by 0.955 inches is equal to 157 pixel. Thus, implying there are approximately 157 pixel per every 0.955 inches in our image. Using this ratio, we can compute the size of an object in an image. Let's start with the program of distance measurement. First, import all the package which is required to perform operations. First package is imutil. It is series of convenient or function. It is already in the library to perform operations like translation, conversion of images, resizing, sorting, reordering, and these operations can be done. NumPy, it is used to perform numerical operations like addition, subtraction, multiplication in image processing technique. We use argument parse package to get image as argument from the user, and in these we use the function as imread. SciPy, it is used to perform algebraic operation and complex numerical computations. In the next step, we load the image and convert the image to grayscale using color BGR to gray function. Next, we apply Gaussian filter function to smooth the image by removing the high frequency noise. Then we perform edge detection operation to outline the object. In addition to it, we use dilation and erosion technique to close the gap during edge linking in the edge map. We use find contour function to find the possible contours in the image. Then we sort the found contours from left to right with respect to reference object. Third step, explain each contours. Here we loop the contour one by one. If the contour pixel is greater than 100, it will exclude. Otherwise, it will neglect the contour as noise left over from the edge detection process. Finding the bounding box of the contour. Then, next step, we draw the contour outline in green using draw contour function and vertices in small red circles. Before that, we order the contour from left to right using perspective function. Step 4, midpoint. Unpacks our ordered bounding box, then computes the midpoint between top left and top right points, followed by the midpoint between bottom right points. We also compute the midpoint between top left with bottom left and top right with bottom right. Draw the blue midpoint on our image, followed by connecting the midpoints with purple lines. Step 5, pixel per metric variable. We compute the Euclidean distance between our sets of midpoints. dA is height distance, dB is width distance. If our pixel per metric variable has been initialized and if it hasn't, we divide dB by our supplied width, thus giving us our approximate pixel per inch. Step 6, dimensions on image. Here we find the dimensions of an object by dividing the Euclidean distance by pixel per metric value. Then we display the dimension value in inches in the image by putText function, and we display the image using imShow function. Step 7 is the result. So after passing the images in the program, we'll get the following result, in which each of the object is detected and the measurement is shown.
The object detection so far: scale invariant feature transformation, speeded up robust feature from accelerated segment test, corner detection, fast RCNN, you only look once, YOLO. These are the features that we are going to look up in the upcoming slides. The scale invariant feature transformation, also called as SIFT, is a feature detection algorithm in a computer vision to detect and describe the local features in images. Applications include object recognition, robot mapping and navigation, image sketching, 3D modeling, gesture recognition, video tracking, individual identification of wildlife, and match moving. The shift key point of object is first extracted from a reference of two images and then it is stored in a database. An object is recognized in a new image by individually comparing each feature from the new image to this database and finding candidate matching feature based on the Euclidean distance from feature vectors. Finally, the probability that a particular set of features indicates the presence of an object is computed, given the accuracy of fit and the number of probable false matches. Object matches that pass all the tests can be identified as correct with high confidence. These are the steps that include in the scale invariant feature transformation: scale space extrema detection, key point localization, orientation assignment, key point descriptor. Now let's move on to the speeded up robust feature. In computer vision, speeded up robust feature, also known as SURF, is a local feature detector and descriptor. It can be used for the tasks such as object recognition, image recognition, classification, or 3D recognition. It partially inspired by the scale invariant feature transformation descriptor. The standard version of SURF is several times faster than the SIFT and claimed by the authors to be the robust against the image transformation than SIFT. SURF descriptors have been used to locate and recognize objects, people and faces, to reconstruct 3D scenes, to track an object, and to extract point of interest. The image is transformed into coordinates using the multiple resolution pyramid technique to copy the original image with pyramid Gaussian or Laplace pyramid shape to obtain an image with the image size but reduce the bandwidth. This achievement is a special blurring effect on the original image called the scale space and ensures that the point of interest are scale equivalent. The difference is that the SURF algorithm specifies scale space extrema detection by constructing the scale space via distribution changes instead of differences of Gaussian filter. To approximate Laplace of Gaussian, SURF uses the box filter representation. Let's move on to the features from accelerated segment test, also known as the FAST. FAST is a corner detection method which could be used to extract features point and later used to track and map object in many computer vision tasks. Referring to its name, it's indeed faster than many other well-known features extraction methods such as difference of Gaussian used by the Swift, Susan and Harris detectors. The fast corner detection is very suitable for the real-time video processing application because of its high-speed performance. Corners in an input image have distinctive features that clearly distinguish between them from the surrounding pixel. Reliable detection and tracking of corners in images are possible even when the image have geometric deformation. The Harris corner detector used the shift method has good performance, but it is not effective for real-time object recognition due to its long computing time. Now let's move on to the FAST RCNN. The FAST RCNN is nothing but the feature accelerated segment test RCNN. The approach is similar to the RCNN algorithm, but instead of feeding the region proposals to the CNN, we feed the input image to the CNN to generate a conventional feature map. From the conventional feature map, we identify the region of proposal and wrap them into squares, and by using roll pull layer, we reshape them into fixed size so that we can feed them fully into connecting layers. The reason why fast RCN is faster than RCNN is because you don't have to feed 2000 region proportion to conventional neutral network every time. Instead, the conventional operation is done once per image and the feature map is generated from it. Each feature vector is fed into a sequence of fully connected layers that finally branches into two siblings output layers. One that produces softmax probability estimates over k object classes plus a clutch all background classes. Another layer that outputs 4 real valued numbers from each of the k object classes. It has a higher detection quality. The shift key point of object is first extracted from a reference of 2 images and then it is stored in a database. All the previous object detection algorithm uses region to localize the object within the image. The network does not look at the complete image. Instead, parts of the image which have high probability of containing the object. YOLO, or you only look once, is an object detecting algorithm much different from the region-based algorithm seen above. In YOLO, single conventional network predicts the bouncing boxes and the class probability of these boxes. YOLO is a new and a novel approach to object detection. YOLO frame object detection is a recognition problem to spatial separation, bounded boxes and associated with probability. Now let's move on to the ML and DL, which literally means the machine learning and deep learning approaches. Machine learning refers to a system that can learn from the experience, and deep learning refers to a system that learns from the experience on a large data set. Some of the machine learning approaches are Wallace-Jones object detection framework based on hair feature, scale infrared feature transformation, which is also called as the shift, history of orientation grenades, hog feature, and some of the deep learning approaches are regional proposals, single shot multi-box detection, you only look once, single shot referencing, neutral network for object detection, RetinaNet, deformable convolutional networks. By using all the features above, this is how we detect an object by using an OpenCV in a computer vision. Thank you.